Okay, so let's continue to look at the chi-square distribution, and at this point we're going to take a look at what the p-value actually means. So in the problem with the M&Ms, we computed the chi-square statistic to be 10.180 because all of the expected counts for the chi-square statistic were at least 5. The chi-square statistic will follow a chi-square distribution. Remember, your degrees of freedom here are always your number of categories minus 1, which is 6 minus 1 to give you 5. And we're always assuming that the null is true here. So in this case, this is the probability that I get a chi-square statistic as extreme as ours, given that we're assuming there's no difference in the distributions, okay? Now notice we have a chi-square statistic with a degrees of freedom 5, and that's still right skewed, and here's my p-value, or the probability that I am going to get a chi-square statistic at 10.180 or more. Now that's really the exact same thing as when we talked about the p-values for all of our other types of distributions. There's not anything different. So there's two ways to find the p-value. You can go ahead and use table C in your in the tables of statistics that you have, and you want to check, you'll want to make sure that you're looking at the one labeled chi-square distribution. Go ahead and look at the degree of freedom of 5. Okay, and since we have a degree of freedom of 5 and our value is 10.180, so notice how it is in between, okay, 9.24 and 11.07. So that's right here. It's going to be a little bit between there, so you're going to kind of estimate between your p-value being 0.10 and your p-value being 0.05. So how you're going to read it is you read the degrees of freedom, then you find your chi-square statistic in here, and then you go up in order to find your probability or your p-value. Now, since our p-value is between 0.05 and 0.1, we know it has to be greater than 0.05. Therefore, we're failing to reject the null, and we don't have sufficient evidence to conclude that the company's color distribution is incorrect. I would highly suggest using your graphing calculator in order to get your p-value. I think it's much simpler, and you already know how to do this after doing your TCDF and your normal CDF. So what you're going to do is you're going to go to second and then vars, and then when you scroll down, instead of doing your TCDF or your normal CDF, you're going to scroll down to chi-squared CDF. And you're going to do the same thing that you did before. You're going to write your chi-square distribution. So in this case, our chi-squared value is 10.180. Since we're checking to find the probability that it's greater than the above bound, so it's your lower bound and then your upper bound. Your upper bound is going to be 1,000, and then notice here we have to include the degrees of freedom. The degrees of freedom was 5. So that's important because every chi-square distribution is going to look different, so you have to show that degrees of freedom, and it gives you your p-value here of 0.07, which is similar to what we talked about. We said it was going to be somewhere between 0.05 and 0.10. Before you perform the chi-square goodness of fit test, here are the conditions and assumptions that you'll need to check. We kind of already talked about this, but they're not any different than what we've talked about before. You need to have a simple random sample. In this case, instead of proving the normal condition, we're going to say that all expected counts have to be at least 5, and you must show the expected counts on your problem. So as part of your answer, just include those. Independence condition is that the population is still 10 times the sample size. Before we start using the chi-square goodness of fit test, there are two important things you have to remember. The chi-square test statistic compares the observed and the expected counts, okay? So be careful with that. Don't ever try to compare the proportions in each category, because remember, it's a categorical variable that we're dealing with. So we're comparing the counts. Are the counts the same or are the counts different? When you're checking the large sample size, the independence condition, be sure to examine the expected counts, not the observed counts. So show your expected counts. So make sure, okay, once again, that you're showing your observed count, make sure you're showing your expected counts as part of your problem. All right, so let's just take a look at what carrying a chi-square test, goodness of fit test looks like. Suppose conditions are met to determine whether a categorical variable has a specified distribution in our population of interest, or basically what we're looking at. As a proportion of the individuals, we're going to perform a chi-square test. So after you state your conditions and the name of the test, you're going to state the null and alternative. So the null is that the stated distribution of the categorical variable is correct. Or you can just say the distribution of M&Ms is correct. Make sure that you're putting that in context, okay? It's very, very important that you put that in context of the problem, because you could say the same null and alternative for every single question and it doesn't tell your reader what you're talking about. Okay, the alternative is that the stated distribution of the categorical variable or the stated distribution of the M&Ms is not correct. And it doesn't mean every single solitary count is off. It could just mean just one of them is off. All right. Then what you're going to do is find the expected count in each category, assuming that the null is true. Then calculate your chi-square statistic, and then go ahead and write your conclusion. Now, when you calculate your chi-square statistic, like I said, you can use your graphing calculator, but you're going to have to show two of these numbers plugged in. Okay, and then I always just write plus ... and then what is your other observed minus expected squared divided by your expected. Okay, then you're going to find your p-value. So make sure you include your probability statement. So the probability that your chi-squared value is greater than whatever you got, and then your p-value. So the same thing that we've talked about before, and then you're going to include your conclusion. Make sure that you include the degrees of freedom, so it's your number of categories minus 1. So let's just take a look at an example of putting all this into practice. So in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for the youth leagues in Canada, players born in January will be competing against players up to 12 months older. The older players tend to be bigger, stronger, and more coordinated, and hence they get more playing time, more coaching, and have a better chance of being successful. So we want to see if a birth date is related to success. Now this is judged by whether a hockey player makes it into the NHL. So a random sample of 80 NHL players from a recent season were selected and their birthdays were recorded. Let's take a look at that information. So you'd always be given information about your observed counts. So the below table summarizes the data on birthdays for these 80 players. So the number of players from January to March is 32. Notice this is in counts. April to June is 20, July to September is 26, and October to December is 12. The question then says, does these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? So that's basically saying, is the distribution, are they the same all 4 quarters? Now this is a goodness of fit test because we're checking to see how well does this data fit what it should be. So how many birthdays should be, each of these are going to be 3 months. How many birthdays should be in the first 3 months, the second 3 months, the third 3 months, and the fourth 3 months? Okay, so let's go ahead and get started. Your first step is always going to be find the expected counts. Now notice this question does not give us what the proportions should be, but we assume that all birthdays are equally likely. Okay, so we're assuming that they're all evenly distributed across the 4 quarters of the year. So therefore, that means that since I had a total of 80, okay, always find the total. I should have written that first. Okay, taking the total of 80 divided by 4 because I have 1, 2, 3, 4 different categories, and that gives me 20. So I find it very helpful to put the expected counts right underneath it. Okay, and then if you add up the total, they should all add up to 80. And just be careful, do not round the expected counts. Okay, this case they're nice and pretty, but they're not always going to be, so do not round those expected counts. So that's step number 1, find your expected counts. Okay, step number 2 is now everything that you've done in the past. Our state portion tells the reader what you're doing. We're going to use a chi-square goodness of fit test, and make sure it's very important. Don't just say chi-square, you need to say goodness of fit to see if the birthdays of all NHL players are evenly distributed among the 4 quarters of the year. Since no significance level was specified, we're going to use 0.05, and remember that's what you always use if nothing is given. Okay, so our state. Now let's do our plan. We've already stated that we're using a chi-square goodness of fit test. You only need to do that once. Let's do our conditions. We have a simple random sample of NHL players. There are more than 10 times 80 or 800 NHL players, and make sure that you're labeling this simple random sample, independence, and then we don't have the normal condition, we have the large counts condition, where all expected counts are at least 5. Make sure that you show those expected counts as part of your problem. Now that we've done that, we can move on to the null and alternative. Notice the null is that the birthdays of all NHL hockey players are evenly distributed, or the distribution, as long as your wording says something like that, the distribution is what it should be for NHL hockey players. The alternative is that it's not evenly distributed, or that at least one of the categories is different. So I would just stick to the distributions are the same, and then the second for the alternative is that the distributions are not the same. Now here's the part where we get to use our graphing calculator. Okay, so the next thing that you're going to want to do is you're going to want to find your chi-square statistic. So you can do this all on your graphing calculator. Okay, so I highly would suggest doing it on your graphing calculator and then just writing 2 of the different observed minus the expected. So in this case, sorry, I'm just going back to get them. We have 32 and 20 and 20 and 20. So let's just use those 2 in order to write our chi-squared statistics. So 32 and 20. Okay, so we're going to write, remember, it's your observed minus your expected. So we observed 32 minus the expected of 20 squared all over the expected, which is 20, plus your second one, which is 20, was our observed minus our expected of 20 squared all over 20. Okay, and you don't have to write the rest of those out. So remember then what you're going to do is in list 1, you're going to put your observed. In list 2, you're going to put your expected. Then you're going to go to stat. Then you're going to go over to calculate. And then from there, you're going to go to the chi-squared. Make sure you're doing the goodness of fit test. Since there was 4 categories, the degrees of freedom are going to be 3. And hit enter. Once you do that, you're going to get your chi-squared statistic to be 11.2. Now, you're going to have to write that information out and then the probability statement. The probability that chi-squared is greater than 11.2. And you're always going to do greater than for your chi-squared statistic. And that gives you 0.0107 for your p-value. Make sure you've included your degrees of freedom somewhere. In this case, it was 3. So see how it's not that much work? It's kind of nice. So now we can write our conclusion. Because the p-value, 0.011, is less than alpha, we reject the null. Okay? Now, there is sufficient evidence to show that the distribution of birthdays of NHL players is not evenly distributed across the 4 quarters. Now make sure for that one that you are showing that in context, okay? It's not evenly distributed across the 4 quarters for the year. If there was no difference, this is the interpretation of your p-value. If there was no difference, then the probability of getting a statistic as extreme as ours is 0.011. This is statistically significant at the alpha equals 0.05 level. Okay, so now what you're going to do is take a look at the conclusion that's highlighted in red. this will be different than what we talked about before, because we're not saying that the means are the same or different. We're talking about the distribution of the birthdays is not evenly distributed. And then make sure from here that since we rejected the null, that you do a follow-up analysis. And with that follow-up analysis, you're going to state which one is the most different.